know that a DC generator has mainly two windings. One is the armature winding, another is the field winding. The armature winding supplies the load the field winding can be excited from a separate DC source in which case this generator is called a separately excited generator. And we have seen that the terminal voltage characteristics, voltage current characteristics of this generator is almost linear. If we neglect armature reaction, then it is exactly linear. If armature reaction is considered, then it drops slightly in a nonlinear fashion for larger values of load current. This generator is very suitable for supplying loads that require constant voltage, but it requires a external power supply. Instead of supplying the field from the external power supply, the field winding can be supplied from the generator terminal itself. We have seen if certain conditions regarding the circuit is satisfied, then the generator develops a voltage across its terminal. This process is called self excitation. And the OCC of the generator looks like this, and the field circuit load line is given by a straight line. So, the generator builds up to this voltage at no load. This process is called self excitation. The output characteristics of this generator, however, is considerably different from that of a separately excited generator, in the sense that initially it behaves almost like a separately excited generator, but as the load current increases, the behavior, the voltage starts dropping, and for large load current actually the curve looks like this. That is, instead of a voltage source, this generator starts behaving like a current source. However, this phenomenon is observed at a current which is much higher than the general load current, and normally the rated current of the generator will be much less than this maximum possible current, and this generator can also be used for supplying loads that require almost constant voltage. There is other possibilities of connecting this field winding. This is incidentally, this machine is called the DC shunt generators. There are other possibilities of connecting the field winding. For example, instead of connecting the field across the armature terminal, it is possible to connect the field winding in series with the armature terminal. In which case this is called a series generator. Just as a shunt generator, it is possible for a series generator to self excite. In order to get open circuit characteristics of this generator, the field winding is disconnected from the supply and excited separately from a separate DC voltage source, and one can obtain the open circuit characteristics, that is the plot of field current versus induced voltage like this. It should be remembered that construction winding wise, the field winding that is connected across the armature terminal of the generator and in series with the armature terminal are fundamentally different, because the field winding that is connected to the across the generator carries very little current, therefore, it is made up of thin wires and the winding typically exhibits large resistance. However, the series field winding is made up of thick wires and it has fewer number of turns and it offers less resistance. The resistance of a series field winding will be almost of the same order as that of the armature winding. For this generator, when the field winding is connected in series with the armature and the load is kept open, if the machine is rotated at a given speed, constant speed, then initially only the voltage due to the residual flux will appear at the terminal. Once this armature circuit is closed through a load, then the current will start flowing. Depending on the resistance of the load, initially this was the voltage, depending on the resistance of the load, some amount of current will flow. Let us say this. However, as the current flows through the series field winding, the series field winding will produce additional flux and if the polarity of the winding connection is such that the series field flux assists the residual flux, then the induced voltage will increase. This will send more current. And in this process the voltage across the generator terminal will build up and finally settle at the point P, where the load line meets the OCC. So, this is the self excitation process in a series generator. It is similar to that of a shunt generator, except that the slope of the load line now includes the armature resistance, the series field resistance plus the load resistance. For this generator we can write the induced voltage E equal to k phi omega and also equal to IA RA plus RAC plus RL, and E is also a function of IA, which is the OCC. This is the OCC and this is the load line. So, the intersection of these two will give the operating point. Obviously, at no load this generator produces very little voltage, which is equal to the voltage due to the residual flux alone. Just like shunt generator, we can also define a critical resistance here. It is that value of the load line slope for which the load line is tangent to the OCC. If the value of RA plus RAC, this is R critical, plus RL is larger than R critical, then the series generator will fail to build up, or in other words, if the load resistance is greater than some critical load resistance, which is equal to R critical minus RA minus RAC, then this series generator will fail to build up. It should be noted that the value of the resistance R critical or RL critical is a function of the rotational speed of the generator. Higher the rotational speed, higher is the value of this R critical. Then for a given critical resistance, for a given load resistance, we can also define a critical operating speed, because the induced EMF is also proportional to speed, below which for a given load resistance this series generator will fail to build up. For example, let us assume that this is the OCC for a speed n1, rotational speed n1. Then the OCC for a different speed N2 which is greater than or less than N1 can be drawn by multiplying the OCC at N1 by the ratio N1 by N2 or N2 by N1. So, let us say this is the load line corresponding to N2, the OCC corresponding to N2. Then it is obvious that while the generator will build up to almost the rated voltage if it is operated at a speed N1, it will possibly fail to build up at a rotational speed N2 where N2 is less than N1. Therefore, for any load resistance RL, we can define a critical rotational speed N critical below which this series generator will fail to build up. These concepts we have discussed in relation to shunt generator, the apply in a similar manner to series generator. We have also seen how to obtain the output or the output voltage versus load current characteristics for a shunt generator. We can apply a similar method here. For that, we first draw the OCC of the generator at the given operating speed. Let us say this is the OCC. On which we superimpose the load line So, at this load with this load the terminal current, the armature current will have this value IA1 and the generated voltage will be VL1. We can plot that point, let us say this is VL1, this is the generated voltage. So, the terminal voltage for a series generator we have seen that E equal to IA into RA plus RAC plus RL, and this is the value of E, and VL equal to E minus IA RA plus RAC equal to IA RL. Therefore, we draw another line with a slope of, this slope was RA plus RAC plus RL and this slope is RA plus RAC. Hence, the drop, so this magnitude represents the drop across the armature resistance. This is IA into RA plus RAC, and the rest of the magnitude is IA RL, which is nothing but the load voltage. So, we see that load voltage, as the load resistance is changed, this curve, the slope, this straight line will remain fixed, but we will have different load lines which will intersect the OCC at different points. However, the vertical distance between the point where it intersects the OCC and the vertical line where it crosses the armature plus field resistance line is the terminal voltage. Therefore, in order to draw the load characteristics of a series generator, one first draws the OCC, which is a plot of induced voltage versus field current, which is same as the armature current in this case, and then on the same graph draws the load line corresponding to armature resistance and the field resistance, which is for any value of load current which is same as the armature current, the terminal voltage for a given value, let us say I1, IA1, this will be the drop IA1 RA plus RAC, and this will be the terminal voltage VL1, which can be plotted for different values of IA, and we can get the VL versus IA, which is the load characteristics of this DC generator. Of course, this neglected armature reaction, which nevertheless can be included, because if we know the equivalent ampere turns of the armature reaction flux, we simply subtract, let us say we want to find out the terminal voltage at a load current of IA1 including armature reaction, then we first find out draw the line and then find out the drop across armature and series resistance, and then from here subtract the armature equivalent armature reaction field current, and then the vertical distance of the OCC at that point gives the, this is without VL1 without armature reaction, this will be VL1 with armature reaction. Obviously, the VL1, if we consider armature reaction, will be less compared to the case where armature reaction is not prominent. One difference of these output characteristics with the shunt generator is that the output voltage varies over a wide range depending on the load current which is expected, because the strength of the field flux is proportional to almost is dictated by the load current, and as the load current reduces, the field flux reduces, the generated voltage reduces, so the terminal voltage also reduces. For this kind of characteristics, series generator is not very much preferred for loads that require constant, almost constant output voltage. However, this principle of series excitation finds application in another type of DC generator, which are called the compound DC generator. As the name suggests, a compound DC generator contains two field winding. One is excited from in a shunt manner, this is called the shunt field with number of turns in SH, as well as a series field. For this, we can write, if this is the terminal this is the voltage across the armature, and this is the voltage, load voltage. We can write I A equal to I S H plus I L, series field current I A C equal to I L, the armature terminal voltage V A equal to induced voltage E minus I A R A, and the terminal voltage V L equal to V A minus I L R A C. It is seen that here the shunt field winding is connected directly across the machine armature terminal. Therefore, this is called short shunt connection. It is to be appreciated that the shunt field turns and the series field turns are put on the same field poles and share the same magnetic path, that is the shunt ampere turns and the series ampere turns, they are in series. So, the net ampere turns that produces the field flux is given by NSH ISH plus NSE IL. For this case, IL equal to IA minus ISH. Or net So, we can define an effective field current for this to be ISH effective to be equal to AT net by NSH, and this will be given by 1 minus NSE by NSH ISH plus NSE by NSH IA. So, we see that the series ampere turns can be expressed in terms of effective field. So, if NSE is greater than 0, that is there is a series winding, we see that the armature current flowing through it will alter the effective shunt field current and hence the induced voltage in this generator. It should be appreciated that the series field can be connected in such a manner that it can either assist or oppose the shunt field flux. Ideally, we should use a plus minus sign here, that is, the series field current may aid or oppose the shunt field. When the series field current assists the shunt field, this is called cumulatively compound. When it opposes the shunt field, it is called differentially compound. Of course, we can also take the effect of armature reaction, in which case ISH effective will be equal to 1 . Normally, the armature reaction flux is expressed as a in equivalent field current, which is represented by IFAR. There is another method of connecting the series field, which is called the long shunt connection. In this case, the shunt series field is connected first, and the shunt field is connected across the load rather than the armature. This is this voltage is the armature terminal voltage VA. So, for this long shunt connection, we can write VA equal to E minus IA RA, and VL equal to VA minus IA R AC, where and ISH equal to VL by RSH, IL equal to IA minus ISH. The net AT equal to N SH I SH plus minus N SE IA, hence IA minus AT of armature reaction. Hence, I effective ISH effective equal to ISH plus minus NSE by N SH IA minus ISH armature reaction. So, these are the here also either cumulative or differential compounding is possible, which is indicated by the plus minus sign. Just like series or shunt generator, it is possible to find out the OCC and the external characteristics of compound generator. The OCC is found in a similar manner as that of a separately excited generator, that is for determining the OCC only the shunt field is excited. Of course, OCC is found out at a particular rotational speed n. From this OCC, it is possible to find out the terminal voltage characteristics of a compound generator. Let us explain the process for a long shunt connection. In order to find out the external, that is VL versus IA characteristics, first draw the field load line with the shunt field resistance RSH. If there is no load connected, then at no load this will be the no load voltage generated VL0, which is plotted here. At any other load current, the corresponding armature current, we can find out the terminal voltage in the following manner. First, let us for any armature current, let us first find out the effective field current, which is given by ISH effective equal to actual ISH. For cumulative compound generator, it will be plus NAC by NSH IA minus ISH armature reaction. First, so this is the actual field current with which we should add the. So, this let this be the term due to let OB equal to NAC by NSH IA for a given IA minus ISH AR and OC BC equal to IA into RA plus RAC. Let us draw a line parallel to the shunt field load line to intersect the OCC at a point P. Now, at P you draw a similar triangle P M N where P M equal to B C and M N equal to O B. Therefore, the terminal voltage at a field at a armature current of IA will be given by the position of the point M, which is OQ. So, for a given IA we can plot that point which gives the terminal voltage. So, in this way we can plot the terminal voltage for different values of armature current and get the output characteristics for both long and short shunt connection and for both cumulative and differential compound generators. If we do this exercise, then we will find the output characteristics, that is the characteristics of the compound generator VL versus IL can have a very wide range of variation. It is possible to choose the NAC by NSH such that the terminal voltage at no load and at full load current are equal. This is called flat compounding. It is also possible for the full load terminal voltage to be larger than the no load voltage. This is called over compounding. And of course, it is possible for the full load voltage to be less than the no load terminal voltage, this is called under compounding. These characteristics are obtained when one uses cumulatively compound generator, but a differentially compounded generator is used, the output characteristics is very different. In fact, it looks more like a shunt generator with very large current, that is the output voltage drops off very fast, and in fact, it behaves more or less like a current source rather than a voltage source. This is differential compounding. Because of this nature, differential compounding is not very much in use. So, the advantage of a compound generator is that the series field turns can be, number of series field turns can be controlled to give a very wide variety of output characteristics for the cumulatively compound generator, and this is practically used almost universally. So, let us look to solve a few problems regarding compound generator. For example, let us consider a compound generator whose rated terminal voltage is 110 volts. The armature resistance R A equal to 0.06 ohm, field resistance R S H equal to 25 ohm, the series field resistance R A C equal to 0.04 ohm, the load consists of a 200 number of 110 volt 55 ampere 55 watt lamps. The field excitation is adjusted to give a rated terminal voltage of 110 volt. Then find out for long shunt connection, long shunt what will be the induced voltage E and the armature current I A, and B for short shunt connection what will be again E and I A. So, in order to solve this problem, let us first find out what is the load current. Load current I L equal to load power P L by V L. Now, it has been mentioned that the load consists of 200 numbers of 55 watt lamps. So, the load power is 200 into 55 watts and the terminal voltage is 110 volt. sorry, this gives me 100 ampere. So, load current in both cases is 100 ampere. So, for the short, let us see how the short shunt connection looks like or long shunt connection looks like. This is the motor, and this is the load. This current is 100 ampere, this voltage is 110 volt, this resistance is 25 ohm. So, IF equal to 110 by 25 equal to 4.4 ampere, IA equal to IL plus IF equal to 104.4 amperes, EB E equal to VL plus RAC plus RA into IA equal to 120.44 volt. This is for long shunt. For the short shunt, the armature terminal voltage equal to 110 plus series field resistance into load current, field current IF equal to VA by RSH, which is 4.56 amperes. So, IA equal to IF plus IL equal to 104.56 ampere, and EA equal to VA plus IA RA, which comes to 120.27 volts. So, that is how we can find out different parameters of compound generators. Thank you.